Okay, so today we will continue and finish the short overview of the paper for the micropore fluid in a system of thin pipes. So last time we did some consideration of when you put the problem in the non-dimensional settings and you compare the parameters that appear with regards to epsilon, then you can obtain different models. And of course the most interesting one is when you have strong coupling. So in this case we will consider the construction furthermore. So if you remember, we had a elliptic problem which we solved via Lax-Milgram theorem. So that was more or less easy. So now we'll do a construction of the asymptotic approximation in the Ethereal layer and connect that in some way to the approximation away from the interior layer, from the junction, and do a matching procedure as we did for the Newtonian case, and see what happens. So first, here you have construction of the asymptotic asymptotic approximation. So in the case of strong coupling, let's put here. Okay, so let's write down a bit to compare with it's quite similar to what we did for Newtonian fluids, but let's go through the procedure once again. So, oh yeah, I forgot to mention, we will have next time, I planned to have one more lecture on system of thin pipes for power law fluids, which Jean knows much more than me about. But there's an interesting paper from 2016 that I wanted to go through. It's not standard like this. And after that we'll have 2 weeks break because we have exams and I'm a bit busy during that period. And then we will continue afterwards. So this is the plan. So like in the case of classical classical Newtonian fluids. So here we also expect, which this is of course reasonable to expect, that you have different behavior when you have a thin pipe without any variations in the pipe, and a junction which basically here you will have a different problem. So here we also expect that the fluid so exhibits different behavior. I don't know, I think there's an U missing. I think it's like this. In the vicinity of the junction and far from the junction. Okay, so we thus present So the construction of the interior layer, which was, if you remember, up to in x1 direction, I think minus epsilon ln 1 over epsilon, something like that. Interior layer correction. So in the most interesting case where you have the strong coupling. The most interesting case. 3. So of course, I think I mentioned this last time. So the asymptotic solution far from the junction. So far from the junction. Omega epsilon 0, which is epsilon omega 0, is given in the form. So all the notation is kept from the classical case, Newtonian, so I won't repeat it. So it's given only when it is necessary. So it's given in the form, as I mentioned last time, the micropolar Poisson solution. So you have u epsilon I given as u epsilon 1 I E1. So this is to be expected, but the micropolar, in order this to make sense, the micropolar components that need to be non-trivial are the second and the third one. So, but the first one is trivial. So v epsilon I, so it's v epsilon 2I E2 plus v epsilon 3I E3. So this is the, as I mentioned, the micropolar Poisson solution. Okay, so this is of course generated by the following system. I will write it down. It's not so difficult. So the following system. So these viscosities time Laplace over x star I u epsilon I 1 plus dpi over dx1 I. I'm writing this I here, but it's of course in every pipe we have the same. So E1 is 2 mi. So you have, are you guys okay? So V3 over x2 minus V2 over x3. Okay, and then you have minus CA plus CD. So Laplace v epsilon I minus C0 plus CD minus CA gradient x star I divergence star I epsilon I. Okay, plus 4 dr v epsilon I, which is equal to 2 dr rotation of x star I u epsilon 1 I. So this is of course posed in the cross section. So b epsilon I. Okay, the boundary conditions are as usual. I mean, in this consideration, so everything is 0 basically. So we have no slip and no spin. So we have this u epsilon 1 I equals to 0, and v epsilon I equals to 0 on the boundary of each cross section. And it is trivial to see that this pi is given in this form. So q0 plus qi minus q0 over li x1i. Okay, this is for, we know this very well, for the Micropoiseuille solution, everything is more or less easy, but you need to, as before, consider the condition in the interior layer, I mean the system in the interior layer. Of course, you have the correspondingly raised problem, and for that you would also need to prove the corresponding result of exponential decay, existence, and uniqueness. However, it was fortunate that this was already done by Fabio Vittoriano e Silva, I think, some years ago. So this result was just used to implement this procedure. So we denote the interior layer by the following. So G epsilon is omega epsilon 0 union with, so G epsilon I equals 1 to m. Okay, where G epsilon I, if you remember, this was, I think the same notation was used before. So this G epsilon I was x1i, x star I from omega epsilon I, such that this x1 was coming to minus, oh yeah, it was minus epsilon ln epsilon. I had one extra minus. So this is your interior layer. And if you remember, I will repeat the procedure, but I think it's good to go through it in this a bit different setting. So passing to the fast variable, passing to the fast variable, y is x over epsilon, and substituting, so substituting u epsilon is epsilon squared v x over epsilon, q epsilon, so you have the velocity, the pressure is of order epsilon, x over epsilon, and v epsilon is epsilon z of x over epsilon. So So if we substitute this, notice that this is not of the same degree. So usually it is, but in this setting it works only in this form. So into the governing system. So we obtain the following. So the following linear problem, it's not hard to write. So we have minus ni plus ni r plus, I denoted it by v, okay? Plus gradient phi is 2 ni r, rotation z, divergence v is equal to 0. Of course, this means that usually for the Poisson solution, you just rescale the second and third variable. Here all three are rescaled. You have a problem posed in an infinite domain. So this is important. So minus CA plus CD plus Z plus C0 plus CD minus CA gradient divergence Z plus 4 ni r, z is 2 ni r, rotation b. Okay, so you can denote this by 14. The system for, I didn't write it down, but the system for the Poisson solution is denoted by 13. So if I reference it, that means that. So this is posed in the domain. So G infinity is omega 0 union with the m pipes, well, infinite pipes, omega infinity I, where this omega, so consisting of the junction omega 0 and the infinitely long pipes. So the infinitely long pipes omega infinity I. So we write it in this way, y1i, y tilde I from R3. So y1i is bigger than 0. Y tilde I is y2i, y3i. From BI. Okay, of course need to supplement it with the corresponding conditions. Here it's natural that everything is 0 on the boundary of G infinity, and that you have the asymptotic condition that V and Z go to the Poisson solution in each pipe. So the boundary conditions. Read in the following way. So V and Z is 0 on the boundary of G infinity. So this is the whole boundary. And you have the asymptotic condition that Vz go to Ui, Vi in each of these infinitely long pipes. Okay, so this is 15. Of course, as I mentioned, so this here, so you epsilon I, which is epsilon squared Ui, x star I over epsilon, the epsilon I is epsilon Vi, x star I over epsilon. So they are given by 13, which was the system for the micropolar plus A solution. Okay, so as before, there is some work to be done regarding the existence, uniqueness, and exponential decay. As I mentioned, this was done, I think, in 2005. Okay. We did a similar result. I mean, it's not really similar, it's completely different. But for the linear problem for the non-steady case, where you have quite some different problems, but you also have this exponential decay. And what I'm attempting to do now is apply this result to the non-steady flow of a micropolar fluid in a system of thin pipes. Something was done. Two very, very long and hard to read papers were published by Panasenko and Pileckas, two big names in this area, and I think 2015 for the Newtonian case, so for the non-steady Newtonian case, and now I'm attempting to do this for the micropolar. So most methods can be adapted, but you always need to be careful about the approach because of this coupling, and things can be a bit more complicated. So that's just a side note. So by analogy, with the classical Newtonian case. So the problem uh, 1415. So it's called the micropolar micropolar, Lirace problem. So as I mentioned, the existence, in case you need it for something, I think it was done in a more general form there, but anyway, so the existence, for example, I'm sure that he incorporates nonlinear terms, quite sure. So the existence, uniqueness, and exponential decay result. So it can be found in this paper that I mentioned. So it's Lirace's problem for viscous incompressible micropolar fluid. So this is from Journal of Mathematical Analysis and Applications, 2005. So anyway, so what does this result say? Well, we are interested, of course, in the existence of uniqueness, but the exponential decay is what is most crucial here. So you have the following. So thus, no problem. (1415) has a unique solution. So a unique solution so satisfying the following estimate. So I have v in the variable y minus ui y tilde I. So more or less similar as before, but let's check. So gradient vy minus gradient ui. So this is for the velocity, and for the microrotation you have z and vi plus gradient zy minus gradient vi okay, plus pi of y minus qi minus q0 over L1 y1i minus you have this stabilization constant given in this form. So this is less than equal to c e to the minus tau y1i. And this holds for every y in omega infinity IR, which is y in omega infinity I, where y1i is bigger than r, and y1. Okay, we should just write this down, but whatever. So c and c I infinity are positive constants, and tau is bigger or equal to 1. Okay, so you have this result. And then, of course, I will write down the approximation in the Ethereal layer and then do the matching procedure as before. So the approximation in the interior layer so interior layer G epsilon is given by by the following. So v epsilon of x is epsilon squared v of x over epsilon. P epsilon of x is epsilon p of x over epsilon, and z epsilon of x is epsilon z of x over epsilon. Of course, you cannot explicitly compute this, but it is as it is. You obtain it in this form. You just have the existence uniqueness and corresponding decay properties. So as before, as I mentioned, you need to somehow match this interior layer and the Poiseuille solution that is constructed away from the junction, so away from this interior layer. So we do this in the following way. So notice that as a side note to something I'm trying to do with Jean, it's important that this junction is of order epsilon, and these pipes are also of order epsilon. But for example, if you had a junction which is of order epsilon squared, it's a problem. So it's very important to consider all these aspects of epsilon, especially in the not only in this solution, which will of course depend on the geometry of the domain, but in the domain itself. So it's not the same if you just switch something a little bit. So just as a side note. So the approximation in the interior layer so given in this form, B epsilon, B epsilon, and Z epsilon. So, and the approximation so U epsilon I, B epsilon I, and V epsilon I. So this is away from the junction. They are matched, of course, asymptotically. So this means, of course, that as epsilon goes to 0, and I'll denote it by small v epsilon. So if you remember, this was the part of the pipe when you removed the interior layer. So, x1I, x tilde I from omega epsilon I. So you have minus epsilon ln epsilon. x1I li. Okay. However, you have the error on the interface between v epsilon I and g epsilon I. So you need to correct this, and you do this in a similar fashion as for the classical case, but let's repeat the idea. So, however, on each interface, gamma epsilon I, which is x1I, x tilde I, from omega epsilon I, so of course when x1 is minus epsilon ln epsilon, between g epsilon and v epsilon I. So g epsilon was the domain up until this value, if you remember. It holds, so you have the following. that V epsilon is, of course, you can write it in this way, so U epsilon I plus this error, which you want to be as small as possible, of course. So we define it in, so it's given basically in this way, E epsilon I of x tilde I, it's epsilon squared, V of minus ln epsilon x tilde I over epsilon minus ui x tilde I over epsilon. Okay. And z epsilon is in a similar fashion, so you have v epsilon I plus, let's denote it by f epsilon I, which is given in this way. So it's epsilon, note the difference. Z of minus ln epsilon x tilde I over epsilon minus vi x tilde I over epsilon. Okay. So what do you have now? You have the following. So we now have the following. E epsilon I is less than equal to, so I will denote this by 17. Of course, I forgot the exponential decay is should be denoted by 16 anyway. 16 exponential decay. So it's less than equal to c epsilon squared e to minus tau absolute value of ln epsilon. And it can be shown that this is less than equal to c epsilon to the third, which will be good enough for our estimates. And f epsilon I in the same manner is less than equal to c epsilon e to the minus tau epsilon. So this is c epsilon squared. So of course, since the difference in the order is 1, it will also be here. So epsilon to the third and epsilon to the square. Okay, so in order to define your, how do I call them here? I think residual correctors or something like that. Anyway, to obtain this existence result, not necessarily uniqueness, for the divergence equation, which will define these correctors, which will take into account these errors, you need to check the compatibility condition. So you have the following. Next we have, so denoted by 18, the compatibility conditions need to be checked on the interface. So this integral e epsilon I times e1I. So this will need to be equal to 0 in order for a problem to have at least one solution. So I will write, if you remember from the classical Newtonian case, you had the solution, these correctors defined as solutions of corresponding divergence equations, which is usual if you've done some, if you read some results about justification of the models. Usually when you construct asymptotic approximations, the residual in the divergence equation, is not small enough, and then you need to construct this corrector, which is basically a solution of some divergence equation. And you always need to check these compatibility conditions, which will impose usually a lot of additional conditions on your initial assumptions. So Here you obtain with this change of variables the following. So epsilon to the fourth, the integral over vi v minus ln epsilon y tilde I. So this is going to plus infinity minus ui dy tilde I. So from the condition 15.2, which is the asymptotic condition for the linear problem, that v goes as y goes to infinity to ui, this will be equal to 0. And now when you have this, so you can now introduce h epsilon I as the solution of the problem. So as I mentioned, it's the solution of the divergence equations. So divergence h epsilon I is equal to 0 in v epsilon I. H epsilon I is equal to minus 1 over epsilon squared e epsilon I on this omega epsilon I, and h epsilon I is equal to 0 in the rest of the boundary. Okay, so if you don't have this condition satisfied, then you don't have the solution, at least one solution of the divergence equations. So you notice that I mentioned, of course, that this problem does not have necessarily a unique solution. So, but this doesn't matter. So this is the best we can do in these kinds of problems. So you don't have uniqueness, but you know that there is at least one solution to this problem 19. Okay, more or less the same. Okay, it's not the same as pressure, but anyway, similar in a similar manner. So you construct the corrector for the micro-rotation residual. So there exists a function g epsilon I such that so you can put it in this way. Just let me check something. It's not. I think it's not necessarily the solution of. Okay. So it's g epsilon I equal to 0. It doesn't matter that the divergence is 0. In v epsilon I, g epsilon I is minus 1 over epsilon f epsilon I on the interface, and g epsilon I is equal to 0 on the rest of the boundary. Okay, you can denote this by 20. So when you have this, your matched asymptotic approximation. So of course you don't need to construct these correctors, but the whole point is that you improve your overall estimate. So if your estimate between, in some function space, between your solution the original solution, which you cannot compute, and the constructed approximation here of order 1 is not good enough, then you haven't really achieved something. So it's always better to at least theoretically construct these correctors. So finally, our matched asymptotic approximation reads the following. So we have V epsilon approximated is epsilon squared U epsilon approximated, where this U epsilon, so it's V of x over epsilon in the interior layer, and U epsilon I, but plus this corrector, so H epsilon I in the rest of the pipe, so V epsilon I. And a similar manner for the micro-rotation, so epsilon V epsilon approximated so I have Z of x over epsilon. This is not I here, just G epsilon. So in G epsilon, V epsilon I plus G epsilon I in V epsilon I. So this is small v, of course, this is the domain. And you don't have corrector for the pressure. So you just have P epsilon I and V epsilon I and big P epsilon in G. So these are the corrections that are needed in order to improve your overall estimate, and they are important from at least a theoretical point of view. So let me we won't have a break, I just want to write down the result for the justification and make some comments. So we have the following. So you have a rigorous justification. Via error estimate. As a side note, we usually do this justification in this way. So you write down the solution, the system for the original solution, the system you derived for your approximation, subtract them, and try to get some estimates using different inequalities, etc. But of course, you can do this verification, justification numerically. But this is something that we are not doing at the moment, but some people do it in that way, which is also okay. So theorem 1. States the following. So we have this result. So let U epsilon P epsilon V epsilon so be the solution of the original problem. So was denoted by 1. And u epsilon approximates p epsilon and v epsilon. So let this be the asymptotic approximation. So given by 21. Okay, when you have this, then the following estimates hold. So we have estimates given in this form. So I don't know if I denoted by 21, but you know what I mean. This is the last thing that I wrote. So usually we scale this up in front by omega epsilon square root, because if you didn't put this, then you can see this note in a lot of papers that any L infinity function will basically go to 0. So this is why you scale this. So epsilon to the minus second, u epsilon minus u epsilon approximate. So L2 of omega epsilon is less or equal to c epsilon square root of minus epsilon ln epsilon. Okay, then omega epsilon minus 1 to the minus 1 over 2. Usually it's expressed in terms of this gradient, so gradient epsilon to the minus second, but it depends, it varies on the paper. Okay, so C. Of course, when you have this, you obtain this via Poincaré inequality for the corresponding thin domain. Omega epsilon. Of course, if you have, this is an important side note, if you have that, but usually it is the function that is 0 at least on the boundary domain that is not of measure 0. I think that's sometimes this is not fulfilled, so you need to adapt it. I think for the temperature it usually is not true. So just a side note, so if you see it somewhere. So epsilon to the minus first, v epsilon minus v epsilon approximate. So L2 of omega epsilon, I didn't write it here. Usually we use L2, H1. Sometimes there are some weaker norms, but it depends on the problems. Not many papers with this. So at least in this way that is constructed. So C epsilon minus epsilon ln epsilon. And for the pressure, have P epsilon minus P epsilon approximate. So L2 of omega epsilon over R. So C epsilon minus epsilon ln epsilon. Okay, so you have these estimates. And I wanted to, of course, this is not so trivial to prove, but we can check it, of course, in the paper. As a side note, I wanted to emphasize this. So with remark 2, so introducing, well, it's in a similar manner, for example, when you have a straight pipe or a curved pipe, you need to consider the boundary layer corrections, construct them in order to improve your overall estimate. Here it's the same basic idea, but you don't need to construct the boundary layer correctors, but only this how they call it here, interior layer correction. So that's the difference. So introducing the interior layer correction. So in the vicinity of the junction. As we did, so that was the H epsilon I and G epsilon I. So improves the constructed approximation. So more precisely, okay, you can denote this by 22. If we just take so the micropolar solution given by 13, we would obtain the following estimates. So I just write down these ones. So I think, let me check. So here you would have just C epsilon, so just C. Here you would have also, I think, just, yeah. So the estimates would be in this form, which are, of course, weaker estimates than 22. So from a theoretical mathematical point of view, it's very important to construct these correctors and improve your overall estimate as much as you can. So this is the more or less classical way in these kinds of problems. Okay, so this was the second part was quite similar to the Newtonian case, and next time I would like to go through something different. As I mentioned, the power law fluids, which I haven't honestly worked with, but I saw a paper that was published by Professor Polok and Pajan in 2016, which has some kind of new ideas, especially regarding the pressure, some results. Maybe Jean will know more. So I would like to go for that, and that will be the next time, and then we'll have the break of 2 weeks, and then we will see after that. Okay, thank you for your attention.